Data structures and basic algorithms. VLSI chip design process can be viewed as a transformation of data from HDL code in logic design to schematics in circuit design to layout data in physical design. In fact, VLSI design is a significant database management problem. The layout information is captured in a symbolic database or a polygon database. In order to fabricate a VLSI chip, it needs to be represented as a collection of several layers of planar geometric elements of polygons. These elements are usually limited to Manhattan features, vertical and horizontal edges, and are not allowed to overlap within the same layer. Each element must be specified with great precision. This precision is necessary since this information has to be communicated to output devices such as plotters, video displays, and pattern generating machines. Most importantly, the layout information must be specific enough so that it can be sent to the fab for fabrication. The symbolic database captures net and transistor attributes. It allows a designer to rapidly navigate throughout the database and make quick edits while working at a higher level. The symbolic database is converted into a polygon database prior to tape out. In the polygon database, the higher level relationship between the objects is somewhat lost. The process is analogous to conversion of a higher level programming language, say Fortran code, to a lower level programming language, say assembly code. While it is easier to work at symbolic level, it can be used by the fab directly. In some cases, the late stages of the chip design process, some edits have been made in the polygon database. The major motivation for use of the symbolic database is technology independence. Since physical dimensions in the symbolic database are only relative, the design can be implemented using any process. However, in practice, complete technology independence has never been reached. The layouts have historically been drawn by human layout designers to conform to the design rules and to perform the specified functions. A physical design specialist typically converted a small circuit into a layout consisting of a set of polygons. These manipulations were time consuming and error prone. Even for small layouts, rapid advances in fabrication technology in recent years have dramatically increased the size and complexity of VLSI circuits. As a result, a single chip may include several million transistors. These technological advances have made it impossible for layout designers to manipulate the layout databases without sophisticated CAD tools. Several physical design CAD tools have been developed for this purpose, and this field is referred to as physical design automation. Physical design CAD tools require highly specialized algorithms and data structures to effectively manage and manipulate layout information. These tools fall in three categories. The first type of tools help in a human designer to manipulate a layout. For example, a layout editor allows designers to add transistors or nets to a layout. The second type of tools are designed to perform some tasks on the layout automatically. Example of Such tools include channel routers and placement tools. It is also possible to invoke a tool of second type from the layout editor. A third type of tools are used for checking and verification. The example of such tools include DRC, design rule checking, and LVS, verify layout versus schematic verify. The bulk of the research of layout of physical design and automation has focused on tools of the last two types. However, due to broad range and significant impact, the tools of second type have received most attention. The major accomplishment in that area has been decomposition of physical design problem into several smaller and conceptually easier problems. Unfortunately, even these problems are still computationally very hard. As a result, the major focus has been on development on design and analysis of Heuristic algorithms for partitioning, placement, routing, and compaction. Many of these algorithms are based on graph theory and computational geometry. As a result, it is important to have a basic understanding of these two fields. In addition to several special classes of graphs are used in physical design. It is important to understand properties and algorithms about these classes of graphs to develop effective algorithms in physical design.